Okay. So there was this guy named Descartes, pretty much a genius in terms of mathematics, has set forth most of the stuff that we've talked about forth in this chapter. But he had this really cool theorem called his rule of signs. His rule of signs. Now, I want to try to give you an idea of what this looks like. If I have a cubic, this is a possible graph, correct? How many zeros or how many solutions does that cubic have? It has 3. And if you look at it, 2 of them are negative, correct? And 1 of them is positive. Now I'm going to draw a different graph. How many solutions does that have? 1, and it is negative, correct? How many solutions does this one have? It has 3 because it's a double root. Very good. And it's positive, 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 right? There's all sorts of different ways that we could draw graphs. But would you agree that every cubic has to cross the graph at least once? Every odd polynomial, it's got to cross the graph at least once. Agreed? How about a quartic? Does a quartic have to cross the graph at least once? No, right? So what can Descartes tell us about just looking at the polynomial that can tell us about maybe where it crosses? And he's got this really cool thing. It's called his rule of signs. It's awesome. The number of positive real roots or solutions or zeros of p of x is equal to the number of sign changes in p of x or less by a multiple, not factor, idiot, by a multiple. YouTube, when I say idiot, I'm referring to me, not anybody else. Or less by a multiple of 2. So what I do is I look at this polynomial here. It starts out with a positive 3 and then goes to negative 4. So that's a sign change. Then it goes from negative 4 to positive 5. That's a sign change. And then from positive 5 to negative 2. That's a sign change. So how many sign changes were there? There are 3 sign changes. So there are 3 positive real roots. Or maybe there's not. Maybe there's fewer. Now there can't be 2. You subtract by a multiple of 2. So I'm going to subtract 2 off, I get to 1. If I subtract 2 off of 1, I would get negative 1. So we stop there. We stop at 1. So there's either 3 positive solutions or 1 positive solution. In order to check the number of negative real solutions, I do the same thing. But I consider p of negative x. I consider p of negative x. Now, how do we determine p of negative x? We plug a negative x in and evaluate the function. So 3x cubed, if I plug a negative in, will it end up being a positive 3x cubed or a negative 3x cubed? Negative 3x cubed. Then if I plug a negative in for x squared, okay, when I square a negative x, it's going to make a positive x squared. And so I'll still keep the subtraction sign, right? Just be minus 4x squared. And then this plus 5x, is it going to be plus 5x or minus 5x? Minus 5x, and then it'll be minus 2. So just to help you out, notice how the odd degrees switched, but the even ones didn't. Okay, so that'll make it quicker for us in the future because we'll practice that today. So look at your new polynomial. Notice how all the terms are negative, aren't they? So are there any sign changes? No. There's no negative ones. You know it doesn't cross the x-axis on the negative side. Never. Descartes has told us by just looking at it. Remember, Descartes doesn't have a graphic calculator. He doesn't have any calculator. So the total number of real solutions then is the combination of the positive and the negative. Suppose there were 3 positive and 0 negative. How many total real would there be? There'd be 3. Suppose there was 1 positive real and 0 negative real, then there would be just 1. There's 3 or 1. You subtract by 2. Subtract by 2. We'll do a couple examples, you'll see. Look at this one, okay? How many sign changes? None. There's no positive real solutions. There's none. Don't even try any. None of them work. Let's do p of negative x. If I do p of negative x, does anything change? No, it doesn't. I get the same thing. Negative x to the fourth minus x squared minus 1. So, what does that tell me? There are no negative real solutions. There are no real solutions at all. We said, can a fourth degree not cross the x-axis? Sure possible. In this situation, if you graphed it, you get something that looks like that. Never crosses. We don't even need to bother finding them. We know from the very beginning. All right. So, now let's consider this part, okay? Suppose that you want to know, so suppose we have like x cubed minus x minus 48, okay? That's like, you hate listing off 48, don't you? Like, you start with 48, go to 24, you go to 6, 4, 3, you go all the way down negative 48. It takes forever, right? Wouldn't it be nice if you knew that you didn't have to try anything above 4? And if you knew you didn't have to try anything below negative 2? Wouldn't it be nice if they could say, hey, we're going to bound it right there. Like, those are your only options. Wouldn't that be nice? It would be. Descartes had a way of figuring that out. He said, we can determine upper bounds and lower bounds. He said, pick a number and let it be positive. If you pick that number, let it be positive, and you divide it through the whole thing using synthetic division, and you come up with all non-negative results, that means that B is an upper bound. That means B is an upper bound. So you don't use this that much in practicality, but when we do, I'll refer to it. You've actually figured out some of it on our own. We did a little bit the other day. But here's the example, okay? I've got a polynomial right there. Everybody admit that you don't know what the solutions are? And by the way, some of you right now are saying, well, it has to be 5 or 1 or negative 1 or 5. That's false. Those are the possible rational solutions. It's totally possible as so we're not talking just about rational options here. We're talking about irrational ones as well. I'm going to show you that there are no solutions that are above 2. If you tried anything above 2, total waste of time. How do I do that? It's easy. Take 2 and divide it in. 1, 0, negative 3, 2, negative 5. And I'll slow down because sometimes when I get through synthetic division, I do a warp speed. So we're just choosing 2 and negative 3. Okay? How you actually choose one for an upper lower bound, you would maybe have to try over a period of time. Okay? We'll give you an example here in a little bit. Okay? So what I do is I drop the 1 and I multiply, add, multiply, add, multiply, add, multiply, add. What do you notice about all my results? They're all not negative. They're all positive. Not only are they all positive, but they're also all non-negative. It's okay to come up with a 0. So non-negative is a statement that includes the opportunity for 0 to exist. So we would say, because all terms are non-negative, there are no solutions greater than 2. Don't try anything greater than 2. It isn't going to work. We don't have time to show you the proof, but it isn't going to work. He was able to develop the same idea for a lower bound. If you take a negative number, we could show that a negative number is in fact a lower bound if when you divide it in, you get alternating signs all the way across. So I'm going to show you that negative 3 is a lower bound. Wouldn't it be worth trying anything lower than negative 3? How do I do that? I take negative 3 and I divide it on in. Sometimes I go too fast. When I walk, like I get into a store and I walk, and you know, my kids are like, "Why are you walking so fast, Dad?" I'm like, "I'm not. You're just super slow." No, it's a track thing. So when you're at a track meet, you have to hurry from event to event, otherwise you miss the meet. So you learn to walk fast, right? Tracksters, you all understand. Drop the 1, -3. Add -3, multiply 9. Add 6. -18. Add -16. Add 48. Add 43. What do you notice about the results? Because all terms alternate sign, there are no solutions less than -3. Okay, let's put it all together. We're going to look at a polynomial, and we're going to identify the number positive real, the number negative real, the total number of real. We're going to identify some choices for rational solutions. We're also going to identify all the solutions. We will go ahead and make use of upper and lower bounds if we need to. We're going to use everything we've used so far, and then we're going to sketch a graph. Now recall, Descartes, Newton, all those guys, they don't have a calculator. So we're going to see how long it would take them using this method. Okay? Who's got a timer? Wants to be my assistant timer? Alex has it. Ready, set, go. How do I determine the number of positive reals? What do I do? How many changes are there in the sign here? There are 2. So I have 2 or 0 real solutions that are positive. How do I determine the number that are negative? And I get P of negative x is negative x cubed, then what? Minus 3x squared, then what? Plus 13x plus 15. How many sign changes are there in that situation? 1. So I know I have 1 negative real solution. So if I have 2 positives, how many total would I have? 3. Suppose I had no positives, how many would I have? 1. Well, let's find them. Anybody know how to factor that? Didn't think so. What are my choices? Sweet. What do you want to try? 1. Let's try 1. 1 cubed is 1. Minus 3 is -2. Minus 13 is -15. Plus 15 is 0. Sweet. 1 works. It's one of my solutions. I divide it in. Drop the 1. Multiply. Multiply. Add. Well, I'm sorry, I'm getting ahead of myself. Add, multiply. Add, multiply, add. So x minus 1 works. And we got x squared minus 2x minus 15. Does that factor to what? X minus 5x plus 3. So what are my other solutions? -3 and +5. Hey, I'm going to stop and smell the roses while I'm at it. Look at what I got. What did I predict ahead of time for the number of negative reals? 1. How many negative real solutions do I have? Exactly. How many total real solutions do I have? 3, how many positive real solutions do I have? And they all come from there. See how this diagnoses it ahead of time? Now we can sketch the graph. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I plot -3, +1, +5. I draw my graph. Sweet. Stop. 3:15. And I was taking my time because we were going together, right? You guys do understand if I was doing my problem on my own, we would cut it significantly. If Descartes or Newton were doing it on their own, I mean, those are two of the greatest minds ever walked the face of the earth, right? Like, they say no calculator, no problem. That's what they say. Exactly. They were too smart for the calculator. Flip it over. Last problem. I don't know, but I've taught with faculty who remember having a wooden calculator at their house that could add and subtract. You better believe it. We've come a long way, man. Yeah. Okay, say it. Tell me more about that, Shelby. Tell me more. What why the response? Multiple times, we got x to the 5th, right? No big deal. Let's roll. Positive reals. Negative reals. Total reals. Choices. And solutions. Looks like a good list. How many positive real solutions might there be? 4 or 2 or 0? I like that. Got to do p of negative x. I get negative x to the 5th. Then what? Minus 3x to the 4th. Then plus x cubed plus 11x squared plus 12x plus 4. How many sign changes? 1. 1 negative real. So suppose that there's 4 positives. How many total? Suppose that there's 2 positive. Then how many total? And suppose that there's no positive real solutions. How many total would there be? Everybody agree that an x to the 5th has to cross the x-axis at least once? Can't get from the bottom to the top without passing through the x-axis, can you? No. Choices. Or do you want to try factoring that? Choices. Man, look at that. Gantz narrowed it down to just 6 choices for us. What a good guy. What do you want to try first? Sometimes when I get to these long polynomials, I don't even bother plugging it in. I just go. And if we just try it, what should we end up as a remainder? What should we have as a remainder? 0. Let's see if we get 0 as a remainder. Drop the 1. Add and I get -2. -2. Add and I get -3. -3. Add and I get 8. 8. Add and I get -4. -4. Add and I get 0. Did it work? It did. It's a solution. Is it possible it could happen more than once? It is. Want to do it again? Okay. It worked again. And I decided to write out the polynomial. Anybody know why I decided to write out the polynomial? Factor by grouping. Factor out the x squared and you're left with Then factor out a -4, and you're left with? Factor out the x minus 1, you're left with x squared minus 4. So x minus 1 times x plus 2 times x minus 2. So what are your other solutions? 1 and then plus or minus 2, right? Look at what you have, folks. How many positive real solutions did you have? 4. How many negative? 1. How many total? 5. They're all listed right there. And if you sketch the graph, knowing what we know, it's got a triple root at 1, a single root at 2, and a single root at -2. All of a sudden, Descartes takes a quintic polynomial, dissects it, confirms his answer, and graphs it like that.